Imagine a spacecraft just hanging out in this cosmic sweet spot.
Mm-hmm.
It's not orbiting Earth, no. It's way out there, like 1.5 million kilometers away.
Yeah, a place where gravity from the sun and Earth does this incredible balancing act.
Exactly. And that's our focus today, the Gaia mission.
It's a fascinating location. It seems almost still, but it's incredibly dynamic, really, and chosen very carefully.
For sure. And for this deep dive, we've got some great material explaining why this spot, a Lagrange point, that's the term, right?
Yeah.
Why it's so crucial for Gaia and, well, other deep space telescopes too.
Right.
So our mission for you today is to really get a feel for why Gaia is parked where it is, what's so special about that spot, and honestly, the amazing effort it takes to keep it there. The precision is just staggering.
It really is. So, okay, let's start with these Lagrange points themselves. Basically, picture the sun and Earth, two big bodies with lots of gravity.
Okay.
The Lagrange points are these specific spots where the gravitational pull from both, plus the centrifugal force on a smaller object orbiting with them, it all balances out.
Centrifugal force. Like being pushed outwards on a roundabout.
Kind of, yeah. It's that outward push you feel. In space, it's the force from orbiting the sun along with Earth. So where all those forces, the pulls and the push meet equilibrium, that's a Lagrange point.
So it's like finding the perfect spot where you don't get pulled too hard one way or the other. A place to stay relatively stable.
That's the idea. Relatively stable. There are 5 of them, L1 through L5.
5, okay.
Yeah. L1, L2, and L3 are lined up with the sun and Earth. L1 is between us and the sun, L2 is behind us, L3 is on the far side of the sun.
Got it. And L4 and L5.
Those two form equilateral triangles with the sun and Earth. They lead and follow Earth in its orbit, and what's really cool is that lots of planets have asteroids hanging out near their L4 and L5 points.
Yeah.
Jupiter's a great example. It's got thousands of these Trojan asteroids, basically traveling companions in its orbit.
Wow, thousands. Like a cosmic entourage. That's wild.
Isn't it? But Gaia, our star mapper, it's not with the Trojans, it's at L2.
L2.
Right.
That's the 1.5 million kilometers behind Earth from the sun's view.
Correct. And L2 offers some really key advantages for looking deep into space. For one thing, the thermal environment is very stable.
Really?
Meaning, because the Earth and Sun are mostly in the same direction from Gaia's perspective, it can use its sun shield much more effectively. Block out heat and light from both at once. That's super important for keeping its sensitive instruments cool and stable.
Ah, okay. So it gets a nice shady spot to work from, thermally speaking. Any other perks to L2?
Definitely. The perturbing torques are stable, too. Basically, the outside forces trying to nudge it around are pretty consistent and predictable, easier to compensate for.
Makes sense.
Plus, being out there, beyond Earth, gives it a clear view. No Earth or moon constantly drifting through its field of vision, blocking the stars, or, causing stray light.
Okay, that's huge for astronomy. No earthly photobombing.
Exactly. Fewer occultations, less glare, just a better, darker view of the distant universe.
It really sounds like the prime location.
Yeah.
But I remember reading these points, especially L2. They aren't perfectly stable, are they? What's the catch?
That's a really important point, yeah. L2 is technically an unstable equilibrium point. Think of balancing a pencil on its tip.
Right, it'll fall over with the slightest nudge.
Exactly. So spacecraft don't just sit at L2. They actually fly in these special orbits around L2. They're called halo orbits, or sometimes Lissajous orbits. They're sort of stable paths near that unstable point.
Okay, so they loop around it rather than staying put.
Precisely. And even in those orbits, they tend to drift. So Gaia needs occasional small pushes from its onboard thrusters to stay on track. Station keeping, they call it.
Like tiny course corrections to keep that pencil balanced.
You got it. Just gentle nudges now and then, based on tracking from the ground.
And Gaia's not alone out there at L2, is it? It seems like a popular spot.
Oh, very much so. It's become a go-to location for major space observatories. WMAP was there, mapping the Big Bang's afterglow. Herschel and Planck observe the infrared and microbye sky from L2. And right now, besides Gaia, the James Webb Space Telescope is there doing incredible work.
Of course, Webb.
And there are more planned. ESA's got Euclid, Plato, Ariel lined up. NASA has the Roman Space Telescope, formerly WF or IRST. L2 is definitely the place to be for cutting-edge cosmology and astronomy.
It's like the downtown district for universe observation. So Gaia launched back in December 2013. How long did it actually take to get out to L2?
The journey itself took about 6 months. After launch, it used its own thrusters over that time to fine-tune its trajectory and then carefully insert itself into its operational orbit around L2.
6 months.
No.
And arriving was just the start, like you said. That station keeping is ongoing.
Absolutely. Ground control monitors its position constantly, calculates the drift, and commands those little thruster firings when needed. It's a pretty much standard procedure for any mission at a Lagrange point.
Okay, so keeping it at L2 needs work. But the documentation we looked at really hammered home the need for knowing exactly where Gaia is and how fast it's going.
Hmm.
Why is that precision so critical?
Ah, yes. This is absolutely fundamental to Gaia's main job, making that ultra-precise 3D map of the Milky Way. It measures star positions and movements.
Right, parallax and proper motion.
Exactly. And to measure parallax, that tiny apparent shift in a star's position as Gaia orbits the sun, you need to know the baseline of your observation triangle extremely well. That baseline is essentially Gaia's orbit around the sun.
Okay.
So we need Gaia's distance from the sun very, very accurately. Now that breaks down into two parts, the Sun-Earth distance, which we know pretty well, and then the Earth-Gaia distance. That second part, the distance from us to the spacecraft, needs to be known to better than 150 kilometers.
Better than 150 kilometers. Over a distance of 1.5 million kilometers? That's tiny. It's like measuring the width of a country with an error less than the length of a street.
It's incredibly demanding, yes. And that's just for the stars. When Gaia looks at things closer to home, like asteroids in our own solar system.
It gets even tougher.
Oh, yeah. For observing main belt asteroids accurately, Gaia's position needs to be known to better than 150 meters.
Meters?
Yeah.
Wow. Okay. That's almost unbelievable precision at that distance.
It really pushes the limits.
Yeah.
So knowing the where is crucial. But what about its velocity? Why does that need to be known so precisely?
Good question. I saw the numbers for that too, and they seemed even crazier.
They are pretty wild. Knowing Gaia's velocity relative to the solar system barycenter, that's the center of mass everything orbits, including the sun, slightly.
Okay, the true center.
Right. Knowing Gaia's speed relative to that is vital because of something called stellar aberration.
Aberration.
Yeah, because Gaia is moving, and light travels at a finite speed. The direction the starlight appears to come from is shifted slightly forward in the direction Gaia is moving, like rain seeming to come at an angle when you run through it.
Ah, I get it. So you need to know your own speed perfectly to figure out where the light really came from.
Exactly. To correct for that effect and get the true position of the stars, we need Gaia's velocity accurate to, well, get this, 1.5 to 2.5 millimeters per second.
Yeah.
Yeah.
Millimeters per second. That's slower than a snail moves.
Yeah.
How is that even possible to measure?
It's astonishing, isn't it? And you're right, standard tracking methods, bouncing radar off it or measuring the Doppler shift in its radio signal, they just aren't good enough. Not even close.
So they need something more advanced.
They do. Which brings us to techniques like Delta-DOR.
Delta-DOR.
Mm.
Delta differential one-way ranging. Sounds complex.
It's pretty clever, actually. The operations team at ESOC uses it. Essentially, Gaia sends out a radio signal, like a ping.
Right.
And that signal is picked up by two different deep space antennas on Earth, located very far apart, say, one in Australia and one in Spain.
Right. Widely separated.
Exactly.
Yeah.
By measuring the tiny, tiny difference in the time the signal arrives at those two stations, they can triangulate Gaia's position extremely accurately across the plane of the sky.
Using the time difference.
Yeah.
Clever. But I imagine there are limitations.
There are. It requires having two big ground stations available simultaneously, which isn't always possible. And to get clean measurements, Gaia actually has to stop sending its science data during the Delta-DOR observations.
Ah, okay. So you lose observation time. Can't rely on it solely then.
Correct. Which is why there's another layer, the Ground-Based Optical Tracking Campaign, GBOT.
GBOT. So this is actually looking at Gaia with telescopes.
That's exactly it. This is an effort led out of Heidelberg University with folks from Paris Observatory heavily involved too. They use several pretty decent-sized telescopes, 2-meter class telescopes.
Where are they?
All over for good coverage.
Yeah.
There's the VST in Chile, the Liverpool telescope on La Palma in the Canaries, and others from the Las Cumbres Observatory Network in Hawaii and Australia.
A global network. And they're taking pictures of Gaia.
Basically, yes. They aim to measure Gaia's position against the background stars down to an accuracy of about 20 milliarc seconds. That's an incredibly precise angular measurement. They use the International Celestial Reference Frame, the star coordinate system, as their backdrop.
But Gaia must be incredibly faint from Earth.
Right.
And moving. That sounds really hard.
Oh, it's a huge challenge. You nailed it. Gaia is faint, about magnitude 21. That's really dim. And from our perspective, it seems to crawl across the sky. But for precision tracking, that motion, about 0.04 arcseconds per second, is actually quite fast to pinpoint accurately against the stars.
So how does the GBOT process actually work day to day?
Well, the flight dynamics team at ESA sends out weekly predictions ephemerides of where Gaia should be.
Okay.
The GBOT team takes those predictions and generates finding charts for the telescopes. The telescope operators then take sequences of images of that specific patch of sky.
Hoping to catch Gaia in the frame.
Exactly. Then the GBOT team processes those images, identifies Gaia, measures its precise position relative to the reference stars, and sends those measurements back to ESA.
And ESA uses that data.
To refine the orbit calculations even further, it's this constant feedback loop between the space agency predicting the orbit and the ground telescopes measuring it. A real international collaboration.
It's amazing. So all this tracking effort results in different orbit files, I gather.
That's right. ESA produces a weekly file, ORB1, mostly based on the radio tracking, the Delta-DOR.
Okay, the quick update.
Yeah. And then roughly once a year, they produce a much more refined file, ORB2. This one incorporates both the Delta-DOR and all the precise optical measurements from GBOT.
And ORB2 is the one they use for the main science.
Exactly. That highly accurate ORB2 is what feeds into the huge computation called the astrometric global iterative solution. That's the complex process that actually combines all of Gaia's measurements over years to build the final star map.
Wow. The scale of this whole operation. It's just mind-blowing. Human ingenuity, really.
It truly is.
And then there's this unexpected bonus that came out of the GBOT tracking, finding asteroids. How did that happen?
Yeah, isn't that cool? It turns out that the regions of the sky where the GBOT telescopes need to look for Gaia generally opposite the sun, near the ecliptic plane. Well, that's also prime territory for spotting main belt asteroids. And because those asteroids are near opposition, meaning opposite the sun from us, they're at their brightest and easiest to see.
So while looking for this tiny, faint spacecraft, they just happened to keep stumbling across asteroids.
Pretty much. They were showing up so often in the images that they started a dedicated GBOT asteroid discovery program back in early 2015.
Makes sense. Don't let good data go to waste.
Exactly. So now, when they spot something moving like an asteroid, especially if it's not a known one, they measure it and report it to the Minor Planet Center.
The official database for this stuff.
Right. It's the central hub for all small body observations in the solar system.
And are we talking about just a few discoveries here and there, or?
Oh, no. It's substantial. The VST telescope alone, for example, can spot anywhere from, say, 10 to 80 asteroids in a single night of GBOT observation.
10 to 80 a night.
Yeah. And roughly half of those, on average, turn out to be previously unknown asteroids.
That's incredible.
The numbers are quite something. As of early 2022, GBOT had observed something like 43,670 asteroids in total. And out of those, over 18,500 were brand new discoveries credited to the program.
Wow. Over 18,000 new asteroids found basically as a side effect of keeping Gaia on track. That's fantastic.
It's a wonderful scientific bonus, absolutely. A testament to keeping your eyes open, even when focused on something else.
Okay, so let's try and wrap this up. We've seen Gaia's out at L2, that special gravitationally balanced spot 1.5 million clicks away. Ideal for astronomy, but needs constant tending.
Right, that's station keeping. Tiny nudges based on incredibly precise tracking.
And that tracking needs to be insanely accurate, better than 150 kilometers for position, sometimes down to 150 meters, and velocity down to millimeters per second.
Yeah, driven by the science goals, which requires these advanced methods like Delta-DOR radio tracking and the GBOT optical campaign.
And GBOT, is a fantastic bonus, ends up discovering thousands upon thousands of new asteroids while it's looking for Gaia. Just amazing.
It really paints a picture, doesn't it? The sheer technical challenge and the unexpected discoveries along the way.
It truly does. An incredible feat.
And it maybe leaves you with a thought, Gaia's whole story, getting to L2, staying there. It highlights our drive to explore, obviously, but also this deep interplay between, cosmic mechanics and sheer human cleverness.
Yep.
So maybe think about this. What other things, maybe systems in space or even things closer to home, seem stable and balanced, but actually need constant, maybe unseen effort just to keep them that way? What else relies on that hidden balancing act?
That's a really interesting question to ponder, finding the hidden effort behind apparent stability.